about the ionization constant. What was that? That is when we show how something ionizes, how something reacts with water. Then we see what is the relationship, the ratio between products and reagents. Do you get a lot of products? Then your ionization constant is high, and high is bigger than 1. Or do you not get a lot of products? So most of the things stay as reagents, and then your ionization constant is low, and low means smaller than 1. Okay, so we looked here, we had 2 acids, and we asked which one is stronger. So they give us the ionization constant, and we saw this one is a very small number, so it means that this one must be stronger. What does it mean? It means it ionizes not completely, but more completely, to give a lot of hydronium ions relative to this one. Okay, now we're going to look at the ionization constant of water. Now this is a very important concept for you to understand. The ionization constant of water. Yes. Now, where's your notes? Holly, where's yours?
Where's your notes?
This is yours, the one without the name. And your other book, you said you're going to bring it this week. Just say this. What are you doing walking around in town until 5:30, 6 o'clock at night? People not in our school. You must be at home, working. You are grade 11. You take science. Your phone.
Yes, man.
Okay, right. So it says there the definition that you must know. This is grade 12 work. The equilibrium constant for the ionization of water is the ionic product of water. We call it the ionization constant of water. Okay, so that is this here. If water split up, or if water reacted with itself, which will not actually happen, okay, water won't dissolve in itself, but if it did happen, you would either get this product if it's split up, or you would get this as products if it reacted with itself. Okay, now water is a very pure substance, and it's also very neutral, so it won't actually do that. But if it did, then you will not get a lot of products. Okay, at all, because it won't want to split up and give you that, or split up and give you that. So the ionization constant for water is a very small number. 1 times 10 to the power of negative 14. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1. That is the ionization constant of water. So water really does not want to split up or react with itself. But if it did, it would have been that. Okay, now this constant is on your data sheet. Okay, given to you. Right. So how do we write this constant again? It is the concentration. Remember, square brackets means concentration of. It's the concentration of the products over the concentration of the reactants or reagents. Okay. But since water cannot dissolve in itself, water's concentration won't change. Water's concentration will always be 1. It will always be the same. So it will be silly to write down over the concentration of water, because water can't dissolve in water. It can't be diluted. So that would have been over 1. So instead of writing that, we just write it like this. Okay. Right, ma'am, you said a lot of things. Must not remember all of it. The only thing you should know is that you find this on your data sheet. Okay. And where will you need this? If you have the concentration of the base, concentration of hydroxide, times the concentration of hydrogen or hydronium ion is equal to 1 times 10 to the power negative 14. Okay. Okay, so that will be given to you on your data sheet. And you must just know how to use it. I'm going to show you how to use it soon. Okay. Now, I said if I say acid, you say what, Courtney? If I say acid, you say? Say again? OH. No. Flornie? Hydronium ion. Okay, the same thing as the hydronium ion is the hydrogen ion. They both mean the same thing. And Tato, if I say base, you say what? Flornie? Say again? No. No. Hope? All right. Yes, Hope. I say base. You say? Sybil? Thank you. Hydroxide ion. Right. So, when you see this, you must think of an acid. Or if you know something is acidic, then you must know the hydronium ion is very, 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 very high. Khali, you must pay attention here. Science week is long gone. Okay. I owed someone lollipops. Was it in this class? No, it was definitely not you. It was Striggles. Right. And the same thing goes if I say base, you must think the hydroxide ion's concentration is high. Those two things go together. So if we look here, I know yours is not in color. Here, and I know this is not very clear. So you can put in here the concentration of the hydrogen ion, a hydronium ion, and this is the concentration of the hydroxide ion. Okay. Now, if we look at something like pure water, we know is neutral. So the pH, you have heard about pH before? The pH is 7, that is neutral. pH scale goes from 0 to 14. So pH of 7 is neutral. There you can see the concentration of the hydronium ion is 10 to the power negative 7, and the concentration of the hydroxide ion is 10 to the power negative 7. And that makes sense to you, because if the one concentration was higher than the others, then it would have been water is a base. And water is not a base. Water is neutral. So these two concentrations must be equal. And you can see they are equal. Now let's go to something like bleach. Okay, bleach is a base. Okay, you know that? Yes, no? Bleach, you can see drain cleaner, bleach, soap, baking soda, things that you clean with, those are all bases. Okay, how do we know they're a base? If you look at the concentration of the hydroxide ion, the concentration of the base, you can see that is a lot bigger than the concentration of the hydronium ion, the concentration of an acid. Okay, so you can see one is a lot bigger than 10 to the power negative 14. Negative 14 is 0,0. Okay, do you see that? Okay, and if we go to something that's acidic, did you know your urine is acidic? Is an acid. Black coffee, tomatoes, soda like Coke and stuff like that. Lemon juice. Stomach acid is close to battery acid. Okay, because your stomach acid must eat away your food and digest it and take it apart. All these things I'll be with you in a moment. They are acids. How do we know they're acids? We can see that the concentration of the acid is bigger than the concentration of the base. Okay, yes. Because your stomach is lined with a stomach liner that protects it. So what happens sometimes if you stress a lot, you get an ulcer. So then your stomach acid becomes too much and it eats away that line, and then you have trouble. So if you stress a lot and you have a lot of stomach ache, you must go see a doctor to sort out your stomach.
Like hiccups.
Yeah. All right. Now there is something very beautiful, scientific-wise, about all of these things. Okay? If you can tell me what it is, you get a lollipop. Something regarding the relationship between the concentration of the acid and the concentration of the base. The relationship between the concentration of the acid and the base. On here. I'm going to zoom in. I'm going to show that one there. No, it's true, but it is not beautiful. What do you want to say, Ona?
They're kind of the same, but then when you get to the acid, they switch.
You're on the right track, but you're not saying what I want you to say. Yes? No. Yes?
Isn't it the OH concentration changes with the acids and the bases? The OH changes with the magnesium ion, and then in bases it switches as well.
That's what Ona said?
No, she didn't say that.
That's what she meant. But no, yes? No?
When the concentration increases.
No? No? Yes?
Okay, I'm gonna try to articulate it as best as I can. So, at the alkaline, wait, are we saying for both like the
Okay, Ona, try again.
The currents.
Yes, Seba?
Ma'am, isn't it when you add the acids and the base, they equal to the constant that we find in the gas?
Prachtig. But it's not adding, but I'll give it to you. If you multiply them with one another. If you multiply, let's take pure water quickly. If you multiply 1 times 10 to the power negative 7 times 1 times 10 to the power negative 7, you get 1 times 10 to the power negative 14. If we take this one, for instance, lemon juice, 0.01 is the same as 1 times 10 to the power negative 1, 2. Ne? Times 1 times 10 to the power 1 times 10 to the power negative 12 gives you 1 times 10 to the power negative 14. So always, 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 the concentration of the acid times the concentration of the base must give you the ionization constant of water. Times, not add. Okay, are you with me? So that is what I give you there. That concentration must always, always, always be like that. Okay, now we're going to go to, before we can do calculations, we're going to go to indicators. Indicators of things that tell you whether something is acidic or basic and where the pH is more or less. Now you get lots of indicators. Like a blueberry, that is an indicator. Your tonic water, I don't know if you ever use. Do you use tonic water? Yes. What for? No, not that tonic. To drink that with the yellow wrapper. That tonic water is an indicator. So if you throw something in there that's acidic or basic, it might change color. Okay? Red cabbage, that is an indicator. So that change, I don't know if you've added red cabbage to food or to water and then it changes a bit of color. Yes, no, red onions are always also indicators. So you get lots of different indicators, but we use these 4 ones in the science lab. There's methyl orange, broomthymol blue, and yes, you must spell them correctly. Now, broomthymol blue has a abbreviation that you can use, BTB, broomthymol blue. We have litmus paper and phenolphthalein. Phenolphthalein. Say it. Phenolphthalein. Okay, now, Methyl orange, I don't have an example of that, but you can imagine in your head it goes from orange to yellow, orange, yellow, orange, yellow, orange, yellow. Then broomthimmel blue, here's broomthimmel blue. It's quite a dark blue, can you see that? Okay, and when you add an acid to it, it changes to yellow, clear yellow. Then we have litmus paper, here I have litmus paper, and you have lots of different litmus papers. This one here is pink, and then it changes to blue, and this one is blue litmus paper that changes to pink. Okay, now what did I say? What is your stomach again? What is in there? Stomach acid. What color will litmus paper turn when it's in an acid? Red, pinkish red. Okay, now part of your digestive system starts in your mouth. When you eat food, your saliva starts to process and take that apart for wherever it is needed. So your saliva is also acidic. Okay? Put it on your tongue. You can all see it's blue.
What
You
about
won't die, I will also do it.
and what about the teeth? Because they first do the process of breaking down these things.
Yeah, first they open the surface area. Then your saliva comes in. Anyone? Anyone? Okay. Can you see mine is changing a bit?
Yes.
Can you see yours?
Yes.
More?
Yes.
More saliva. See your saliva.
He doesn't have saliva.
It's a small pinkish color that it's turning.
He's dehydrated.
Can you see it changes a bit to pink? Now this paper is very old, so it's, as you can see, this is not 100%. Like we, yeah, let's just say it's not 100%. You can see this one here, it already started to change because it was open in the box. So litmus paper is not a very clear or a very precise indication of what something is. Okay? Whereas phenolphthalein is a pink one. Here's phenolphthalein. You can see the nice pink color. And when it is in a acid, it is colorless, and in a base, it turns to that pink. Okay, so that is what we use in science class. And in grade 12, you will do a practical on this. Okay, where you are going to where you are going to let things drop in, and I'll explain that later, and then it will change color a little bit. Okay, so what you must know is you must know when more or less you must use it, and what color it will change, and the name. Okay, now you can see here the pH range of the color change. A low pH, is that close to an acid or close to a base, Rory? A low pH, acid or base? Acid. So we use methyl orange when we have a strong acid that we add to a weak base. A strong acid to a weak base, it will give you a more acidic solution, so then you use methyl orange. Then we can see broomthimmel blue and litmus paper is more or less in the middle range. Okay, this is a bit more to the acidic side, but that's fine. This is very close to 7. So when will we use that? When we have a strong acid and a strong base, or a weak acid and a weak base. You see why you need to know which acids and bases are strong and weak, and. Okay, then you use broomthimmel blue or litmus paper, and then phenolphthalein you use when you are at a very high pH range. That's close to a basic solution. So that is when you have a strong base and a weak acid. Okay. So, for example, if we have hydrochloric acid reacts with a calcium carbonate. Okay, then you get things, blah, 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 blah. Which indicator will we use in this reaction? So, yeah. And why? So for 2 marks, this is a typical exam question. I give you this reaction, then I ask you, which indicator is suitable for this reaction and why? So first of all, you must ask yourself, is this strong or weak? And this one? Go back to page 2. Page 2, I give you a list of the strong ones. I think it's page 2. How do you know it's a weak base? Yes and no. If something has an hydroxide with group 1, like sodium, or group 2 elements, like that, then it is a strong base. If you don't see an hydroxide, then you think it must be weak. Chap. So we have a strong acid, weak base. Which indicator is suitable? The first one, methyl orange. So if they ask which indicator is suitable, you'll say methyl orange. And then why? Because it's a strong acid with a weak base. Okay, you get it? Right. Now we are going to calculate the pH, and then we're going to bring all of these things that we've learned together. Now to calculate pH, you use this formula. This formula is on your data sheet. Now you are in grade 11 now. You haven't done logs just yet, have you?
Yes.
Yeah, yuck.
Calculator has that thing.
Your calculator has that thing. So please take out your calculator that has that thing. If you go to your calculator, you'll see here there's a button that says log. Okay? Now, you know from vectors and newtons and. If you press shift cos or shift tan or shift sin, then it gives you the inverse of that thing, right? Now look at shift log. Press it, shift log. What does it give you? If you press shift log, you get 10 to the power of whatever. So that is literally what pH stands for. pH stands for the power of hydrogen. pH is the power of hydrogen. So 10 to the power of whatever hydrogen's concentration is. Okay, so to calculate log, you're going to say the negative log of the concentration of the hydronium ion. And remember, I told you hydronium ion is the same as hydrogen ion. Those two things is the same. Okay, pH has no units, so you're not going to say newtons or seconds or mole or anything like that. It's just a relationship, and I've said that for you as well. Okay, so let's quickly look how we're going to use it. It says, calculate the pH of a solution where the concentration of the hydronium ions is 10 to the power negative 7 and determine the indicator that will be used in this solution. So we're going to say pH is negative log concentration of the hydronium ion. Okay, and that must be in square brackets because it's the concentration of. Then when you substitute your concentration, when you put in that 10 to the power negative 7, then you lose the square brackets. Then it becomes 10 to the power negative 7 like that. Okay, and I want everyone to practice typing this into your calculator. So you're going to say negative log 10 to the power of negative 7. Tepo, what do you get? Tepo, if you type that in. Seven. No unit, just 7. So, Ona, if you get a solution and the pH is 7, which indicator will be suitable for that solution?
Probably the TB.
Broom-thymol blue will be a suitable indicator. Okay, next one. Calculate the pH and determine which indicator will be used. Wat is fout, Gali? Back to back. You said that or Lesedi said that? Huh? Khali? Don't take away his concentration. And if you calculate that, Zara, what do you get?
3.
Just 3. And the indicator that will be suitable? Methyl orange. Easy peasy? Okay, the next one, same easy one. It will get more difficult, don't you worry. Be careful where you put square brackets, where you put round brackets. That can cost you unnecessary points. Seba, what do you get? 11. And the indicator that will be suitable? And please pronounce it. I didn't check the English. Remember, pH is F. Phenolphthalein. Right, let's make it a bit more difficult. Okay. Calculate the pH of a so concentration of hydrochloric acid and determine the indicator that will be used. Okay. So, planning. How do I do or calculate pH again? It's the negative log concentration of the hydronium ion. Do they give me the concentration of the hydronium ion? No. They give me the concentration of hydrogen chloride or hydrochloric acid. So, Nia Carlo, how can I go from hydrochloric acid to hydronium ion? So we want to go from hydrochloric acid to hydronium ion. There is a reaction that we must write. Yes? What do we call that reaction where we add water? Wait. The ionization reaction. So we're going to show how hydrochloric acid reacts with water. This is a reversible reaction. And then this hydrogen sits there and it gives you the hydronium ion and the chlorine ion. So good, Lano. What is the ratio between hydrochloric acid and hydronium ion? 1 to 1. Okay, so this ratio is 1 to 1. So if this concentration is 0.01, then this concentration will be 0.01. Okay, I'm doing it very slowly now. In the exam, you'll show 1 to 1 and then you'll write down. Okay, now that we have the concentration of the hydronium ion, now we can calculate the pH. pH is negative log concentration of the hydronium ion, negative log 0.01. And what do you get, really? Does it have a unit? No. And which indicator, Khali, will be suitable for this reaction? Yes, it will be methyl orange. Okay. Now let's go up one step further. It says there, calculate the pH of a solution of 0.01 mole per decimeter cube sodium hydroxide solution and determine the indicator that will be used. Okay? Going. So, again, my planning. I must get the pH, negative concentration of the hydronium ion. But I don't have the hydronium ion. I only have sodium hydroxide. What is my plan, Lesedi? How can you go from hydroxide to hydronium? Okay, so not the answer that to my question, but yes, we are going to say sodium hydroxide can split up into sodium and hydroxide. But still my question is, and this is a lollipop question actually, how can I go from there to there? Rory? No. Sia? Seba? No?
What is the question?
How can you go from hydroxide to hydronium? How can you go from hydroxide to hydronium?
It's a base, so it's a hydrogen acceptance, so it is a hydrogen.
Yeah. Sebo?
It's a donor.
Say again? No.
It's a donor.
No.
It's an acceptor.
Yes? No. This is the dissociation reaction. I want to know how can you go from there to there? If I have this one's concentration, how can I go to this one's concentration? I'm saying 2 lollipops.
Whole table, man.
No. No. No.
Tenfold.
No. Yo. Lollipop for me. The question is calculate the pH. Okay, let's do step by step. First of all, like Lesedi said, we must go to sodium hydroxide, and it's not the ionization of sodium hydroxide, it's the dissociation. So it splits up in water to give you the sodium ion and the hydroxide ion. Okay? So if this concentration is 1, then this one will be 1 because the ratio is 1 to 1. But it's not. It's 0.01. So this is 0.01. Then this must be 0.01. But I can't put this concentration in there because it says the concentration of the hydronium ion, not hydroxide ion. So in a way, we must go from hydroxide to hydronium. Courtney?
No, won't you do something with water's concentration?
You're saying, but you're not saying it.
Remind you when I take the H from the
No,
NA.
no.
And you're going to use the
The thing that Courtney says, the ionization constant of water. If we look at this here, the concentration of the hydronium ion times the concentration of the hydroxide ion gives you 1 times 10 to the power negative 14. That will be on your data sheet. That equation there, on your data sheet. Don't have to go study it. Yeah.
I've not seen that thing.
Yeah. After she said it, you said that thing.
Yes, I was thinking.
But she said it first. Okay, so let's check. This is a constant. This concentration we have there. And then I can get this concentration. Okay, so I want the hydronium ions concentration. Hydroxide is 0.01. Remember that square brackets changed to round brackets. Shoni, to calculate that, what must you do with this? Yeah, what must you want to get this? What are we going to do with this? Don't listen to him. He is wrong. No, you're not going to like times. You're going to like divide. That divide there. What do you get if you do that, Tsepo? Tsepo. Tatu? Yes. And now we can calculate the pH. pH is negative concentration of the hydronium ions concentration. Remember, when you fill in the concentration, you lose your square brackets. Yes.
You have to do all of that because the thing is almost over one, and if you look at that thing, it's like,
You won't get that table in a test or an exam.
yeah, but when if you like learning like by heart, you can just
No, you must show this. This question will count 1, 2, 3, 4, 5, 6 marks. What do you get, Hope? 12. Does it have a unit? Does a pH of 12 make sense? Okay, the answer is yes. My question is, why does it make sense? What are we busy with? Sodium hydroxide, is that an acid or a base? You must go study. Yes, it is a base. Rory, weak or strong base? Strong base. Strong base, is the pH high or is the pH low? It's very high. Is 12 high? Yes, because the highest is 14. So a pH of 12 does make sense because we're busy with a strong base. Which indicator is suitable, Sia? Phenolphthalein. Okay. I just want to check something quickly. Okay, grade 11s. I want you to do on page 19, November 2017, question 8.1. Question 8.1, only 8.1. And I want you to start now.